I thanks to organizers for giving me this great opportunity. Today, I'd like to talk about WKB analysis via topological recursion for hypergeometric differential equations. I gave a talk in the case of the waiver equation at the conference held at KITP Santa Barbara in 2017. So I will give her an overview on how I consider the WKB analysis via topological recursion in the case of the waiver equation. So for the waiver curve, the left one, we obtain WGN and we also obtain FG according to the topological recursion. Here, G is a non-negative integer and N is a positive integer. And this WGN corresponds to the correlation functions in the matrix model. And FG is the G's free energy, which is the symplectic invariance. On the other hand, we obtain the waiver equation whose WKB solution is expressed like this form, according to the quantization in terms of WGN. So I want to study the differential equation with a small parameter h bar like this waiver equation. So we start this waiver equation. Then we consider the classical limit of the waiver equation. We get the waiver curve. So by using the topological recursion, we get the WGN, and by quantization, we get the WKB solution by expression by WGN. And so in this way, we consider the WKB analysis by using the WGN. So it's WGN is obtained from topological recursion. So,
elle a dû passer, Sandrine.
Sorry? As I explained above, the quantization scheme tells us the psi. This psi is a WKB solution of that waiver equation. So the quantization, in other words, the quantization connects the WKB solution and the topological recursion. So using this WKB solution and equation 1, we can also find another relationships between the exact WKB analysis and the topological recursion. This is the relationship between the Voros coefficient and the free energy. The Voros coefficient is important gradient in the exact WKB analysis, and whose definition will be given later. And capital F is the generating functions of free energy. Free energy come from the topological recursion. This is the free energy. So
what's lambda in the matrix model?
Sorry?
What is lambda in the matrix model?
Lambda is a parameter of the equation. So WGN contains the parameter lambda. Okay. And so this is the relationship. So the Voros coefficient is expressed as the difference value of the capital F with respect to parameter lambda. And by using this relation, we also obtain the explicit forms of the free energies and the Voros coefficient. So then the above one is the explicit form of free energies. And this is the explicit form of the Voros coefficient.
Sorry to interrupt you, but you're writing explicit forms for the parabolic cylinder functions.
Yeah.
Yes.
Yeah.
So what is G? I didn't understand
G.
why G is there in your expansion in the beginning. In the beginning. Before.
Oh, this is.
Yes. Why do you need G in order to? I can understand the solutions with G equals 0, but what is the meaning of G? Why do you need it?
Sorry,
Asking about the parameter G.
G, yeah.
This does not appear in your equation.
Yeah.
G does not appear in the Weber equation.
Yeah.
So why do you need it in the solution?
Solutions.
I don't understand that.
Yes, thank you.
So tell me, what did you say?
Oh, the FG and G is the so WGN is the correlation. The WGN is the coefficient of the correlation function of the expansion, yeah, and FG equals to WG0, and WG0 is the G's free energy in the topological recursion.
I don't know what the free energy means, but I'm just saying in the solution of your equation, you have to
So the solution,
which does not involve G. And here in
Yeah.
the solution, you have this parameter G.
Solution. Oh, so
Perhaps a quick answer is that it's just an H bar expansion of the WKB. What's relevant in G to N minus whatever she has.
Okay.
If you do the total sum, you're just going to have an expansion part of H bar. And that's just standard WKB, nothing else. It's just convenient way to break apart that expansion into something that then makes the connection to make it fun.
Because you could solve it
Yeah,
without.
of course.
Okay. It's on the bookkeeping device.
Yes.
Okay, thank you. Continue.
sorry. Thank you. So in the case of the Weber equation, we obtain the explicit form of free energies and the Voros coefficient. So the purpose of this talk is to generalize these results for the Weber equation to the case of the Gauss hypergeometric differential equation and other confluent hypergeometric differential equations. So this is the confluence diagram of the family of the Gauss hypergeometric differential equations. So the Weber equation is one of the family of the Gauss hypergeometric differential equations. And these equations are second order differential equations. So we consider these equations and obtain the result obtain the same results. And so then we consider the following equation. The second diagram is a family of the hypergeometric differential systems associated with the two-dimensional Garnier system. So these equations correspond to the partition 5. So this is the partition and corresponds to these systems. So they are differential systems with two parameters, and we make the second variable fixed, and then they are third order differential equations. So we consider the third order differential equations associated with these systems. And then we obtain the result for the green equation of this diagram. So this is the main result. Now for the family of the Gauss hypergeometric differential equations, we obtain the following results. First one is they are realized as the quantum curves for appropriate spectral curves. And note that the spectral curve arising from the Gauss hypergeometric differential equation does not satisfy the admissibility condition of Bouchard and Eynard results. So this is the big difference between the Weber case and Gauss case. So the Weber case can use the Bouchard and Eynard results. And second one is the Voros coefficients are expressed as the difference values of the generating function of free energies with respect to parameters. So in the Weber case, the Weber equation has one Voros coefficient, but the Gauss hypergeometric differential equation has three Voros coefficients, but all Voros coefficients are expressed as the difference values of the generating function of free energies. And the generating function of free energies is uniquely associated with the for given spectral curve. So it means that Voros coefficients are controlled by free energy. In other words, the free energy is more essential quantity. And third one is the explicit forms of Voros coefficients and free energies are obtained. And these results are also, we can also show that these results for 1112, 122, 113, 23, 14 equations. So in this talk, I will explain these results by using the Gauss equation. And then after that, we explain the third order case by using the 1112 equation. So this is the outline of this talk. And first, I will recall some basics about WKB analysis by using the Gauss hypergeometric differential equations. So let us consider the Gauss hypergeometric differential equation with a small parameter h bar. So these two equations is the Gauss hypergeometric differential equations. And we consider WKB solution equation 3. And here S is the summation of h to the power of j times sj. So this psi is the formal solution of the equation 2. So by substituting 3 into 2, we find that this S is a formal solution of the Riccati equation, this equation. And by comparing this Riccati, by comparing the with power of the both sides of equation 4 with respect to h bar, we can find that s minus 1 satisfies this equation. So this equation has two solutions, but for each s minus 1, the other sj are determined uniquely and recursively from this Riccati equation. Then the Voros coefficient, which is an important ingredient to describe the global behavior of Borel-Lizard WKB solution, is defined by this equation 5, where gamma is a path from a singular point to a singular point. So the Gauss hypergeometric differential equation has 3 singular points at x equals to 0 and 1 and infinity. So the path is there are 3 passes, and this is the figure of the path. So this sequence designates the Stokes curve of the Gauss equation, and this wiggy line is the branch cuts of which determine the s minus 1. So gamma 0 is a path from 0 in first seat, from 0 on the first seat to the 0 on the second to the second seat. And gamma 1 is the path from 1 on the first seat and to 1 on the second seat. And gamma infinity is also. So in the case of the Gauss hypergeometric differential equation, we have to consider the 3 Voros coefficients with these passes. And we explained the topological recursion. Here, we also consider that we can also consider the Gauss hypergeometric differential equation. So this is the Gauss hypergeometric differential equation, and as I explained above, the topological recursion start from the algebraic curve. More specifically, start with the spectral curve. So we consider the classical limit of the equation. So that is, we replace h ddx to with y, and then we make h bar go to 0. Then we obtain this algebraic curve 6. So let us consider this algebraic curve, and then we choose x and y like this. So this x and y are satisfy this equation 6 And we call a pair XZ and YZ spectral curve. And here, lambda equals to this, and beta 0 plus minus and beta 1 plus minus equals to this. Note that the x equals to j correspond to j and z equals to beta j plus minus. So the Gauss hypergeometric differential equation has singular point at x equals to 0 and 1 and infinity. So these points corresponds to beta 0 plus minus and beta 1 plus minus, and z equals to 0 and infinity is a point corresponding to the singular point. And
so just to clarify, in physics, we would call this spectral curve, with or without a factor I, we would call it the Hamiltonian in phase space. Yes? It's the graph, the Hamiltonian in phase space with given value of the energy.
Yeah.
Yes?
So yeah, and let x, z, y, z be a spectral curve, and we first define W01 and W02 like this, and for g is non-negative integer and n is non-negative integer, satisfying this, we construct meromorphic differentials Wgn on P1 by following recursive formula. So this is the topological recursion. And branch points are zeros of dxc. We assume that all branch points are simple. And z bar is a local conjugate point of z near branch points. So xc bar equals to xc. And this zi or zz is meaning, this meaning. We use this meaning. And this prime is designate this prime is we do not this sum don't contain the W01. This prime meaning is this summation not contain W01. Yeah. And we define the free energy Fz by the following equation. Then, and where phi z is any function satisfying this equation. And F0 and F1 are also defined, but in a different manner. And for the Gauss curve, F0 and F1 are given by this equation. Then we explain the main result for the Gauss hypergeometric differential equation. So we consider the Gauss curve, this curve, which is a classical limit of the Gauss hypergeometric differential equation. And we define psi like this. And here z equals to zx is an inverse function of x equals to xc. And the integration d is equals to this equation. And here, nu j plus and nu j minus are parameters satisfying the summation is equals to 1. Then this psi is a WKB solution of this equation G. This and this is the Gauss hypergeometric differential equation. So we call G the quantum Gauss curve. And in what parts we use notations nu bar and lambda bar, like this. So this is the sketch of proof of theorem 1. This is the WKB solution. And we proved that the expansion coefficients of the WKB solutions satisfy the Riccati equation after the coordinate change x equals to xc. So we proved that TdZ satisfies the Riccati equation, this equation. So this is the integration of Tm dz. So by comparing like powers of both sides with respect to h bar, we obtain these equations. And this is the so Tm equals to the derivative of this blue part. So by substituting equation 11 into these equations, we found that they correspond to the topological recursion. So therefore, T satisfies the Riccati equation. So the recursion from the Riccati equation equals to the equals to the topological recursion. And then we can obtain the relationship between Voros coefficient and the free energies. So let Fg be free energies for the spectral curve corresponding to the quantum Gauss curve, and capital F is the generating function of Fg. So we sum of Fg from z equals to 0 to z equals to 0. Then we obtain the Voros coefficient is expressed as the difference value of the capital F. So this with 0 is the Voros coefficient with the path lambda 0. So from 0 on the first seat to the 0 on the second seat. So the V0 is expressed as the difference value of the capital F with respect to parameter lambda 0, and as a Voros coefficient V1 is the difference value of the capital F with respect to parameter lambda 1, and V infinity is expressed as the difference value with respect to lambda infinity. So all Voros coefficients are expressed as the difference value of capital F. And this is the sketch of the proof of theorem 2. From theorem 1, and this is the quantization, we can express psi is in terms of WGN as follows. So V0 equals, this is the definition of the Voros coefficient, and we consider we change the x variables to z variables. So then we get this equation. And here we integrate the derivative So we can calculate like this. And here dz equals to this. In this, yeah. And here we use the notation here equals to this, yeah. So the we change the x variables to z variable. So we have to, of course, we have to consider we have to check the passes of the Voros coefficient. So this is the passes of Voros coefficient in the x plane, and x equals to A1 and N2. This is the turning point, and corresponding to the, and z equals to 1 and -1. And x equals to 0 and 1 and infinity. These are the singular point of the Gauss hypergeometric differential equation. They correspond to z equals to beta 0 plus and z beta 0 minus, and beta 1 plus and beta 1 minus, and z equals to 0 and infinity. So the path gamma 0 corresponds to the gamma 0 tilde, which this path is start from the beta 0 minus and to beta 0 plus in the z plane. Then this equals to this. So we can find that this red part equals to this red part because of the variational formula, which is the equation 14 and equation 15. So using this equation 14 and 15, we find that the red part equals to this red part. So this is the Taylor expansion of this equation. So we can prove the theorem 2. And for the quantum Gauss curve, the following relation holds. This is the contiguity relation. So this from lemma 3, capital F satisfies the following 3-term difference equation. So this we use this lemma 3 and the theorem 2. We obtain this equation 16. And similar difference equations are obtained by the other parameters shift. So by solving this equation, we obtain the explicit form of free energies. So this is the explicit form of free energies. So the sketch of the proof is following. This is the contiguity relation, and this contiguity relation is written as this equation. So we need to we can f equals to this inverse operator. So using this red equation, which comes from the definition of the Bernoulli number, then we obtain the explicit forms of free energy. But from this equation 16, we only get the dependence of parameter lambda 0. So we use the contiguity relation for lambda 1 and lambda infinity. Then we can find the explicit form of free energies. And using the explicit form of free energies and theorem 2, theorem 2 is this equation. So we get the explicit forms of the Voros coefficient. So the Voros coefficient are expressed by using the Bernoulli number. And V1 and V infinity can be expressed similarly. Then we explain the third order differential equations, and here we use the 1112 equation, and we explain the results. So the 1112 hypergeometric system is this system, equation 17, and where lambda tilde j is parameters. And in what follows, setting x1 equals to x and x2 equals to t, so we consider this second variable is parameter. And we consider this third order differential equation with respect to first variable. So we consider this 1112 equation to use the topological recursion. We consider the classical limit of this equation. So that is h ddx replaced with y, and then we consider h bar go to 0. Then we get this algebraic curve, and we choose what y equals to z. Then we can also x equals to this. So this x and y satisfy this equation 19. And we call this pair xz, yz a spectral curve, and this equation 20, the 1112 curve. So for this algebraic curve, we define psi as follows, and this is the same one, and for the Gauss hypergeometric differential equation case. And where z equals to zx is an inverse function of x equals to xz, and integration d equals to this one. Then and mu j are satisfied, or the summation of them equals to 1. Then psi is a WKB solution of 1112 equation, which is obtained from the Bouchard and Eynard results. So let Fg be free energies for 1, 1, 1, 2 curve, and capital F can be the generating function of free energies. Then we obtain the Voros coefficient is expressed as the difference value of the capital F with respect to parameter lambda 0. So here also V0 is the difference value of the with respect to lambda 0, and V1 is the difference value of the capital F with respect to lambda 1, and Vt with respect to lambda t. So and this so this equation 1, 1, 1, 2 equation has singularities at x equals to 0, and that is corresponding to the x equals to 0 correspond to z equals to 0 and 1 and 1 over t. So the Voros coefficient this j is this j so 0 and 1 and t corresponds to the singular point of the solution. So yeah, more specifically, the j infinity. So v is a Voros coefficient whose path is from 0 to infinity j. So infinity so this equation and this equation has a singularity at x equals to 0 and infinity, and and the z equals to 0 and 1 and 1 over t corresponds to x equals to infinity. So this infinity j is correspond to infinity t is, so infinity t corresponds to z equals to 1 over t, and infinity 0 is corresponds to z equals to 0, and x equals to infinity 1 corresponding to z equals to 1, and x equals to 0 corresponds to z equals to infinity. And as a Voros coefficient, V1 and Vt can be expressed similarly, so with respect to parameter lambda 1 and lambda t. So from theorem 5 and contiguity relations, we obtain these three difference equations. And similarly, for the Gauss hypergeometric differential equation, we rewrite this equation 22 like this. So we obtain the dependence of the parameter lambda 0, and we use the equation 23. We also obtain the dependence with respect to lambda 1, and by using the equation 24, we also obtain the dependence with respect to lambda t. So we can find that Fg can the explicit form of Fg is expressed like this, but we cannot find the dependence of the parameter t. T is comes from the second variable. So this is the big difference between the second order differential equations and third order differential equations. So only by considering the contiguity relations, we cannot find the dependence on the t variables, t parameters. Yeah. So to obtain the dependence on parameter t, we use the variational formula, this equation 25. So by substituting mu0 and mu1 equals to 0, this 8 is the WKB solution of this. We get this equation 26, and we take the residue of both sides, and we use the variational formula 25, and then we find that this red part equals to the derivative of free energy. So by comparing like both sides, like powers of both sides with respect to parameter h bar, we found that the derivative of free energy equals to 0. Here we use this equation, this blue equation, which comes from the Riccati equation. By using the Riccati equation, we find this equation. So we consider the residue, in the left-hand side, there is no h to the power of odd part. There is no terms. The m is greater than 1. So we find that the derivative of the free energy equals to 0. So we find that the free energy doesn't depend on the parameter t. So we obtain the explicit form of the free energy, this one. And this explicit form and theorem 2, we get the explicit forms of the Voros coefficient of the 1112 equation. So the Voros coefficient are expressed by using the Bernoulli polynomial. Yeah. And V1 and Vt can be also expressed similarly. So for confluent hypergeometric differential equations of second and third order, we obtain the following results. So first one is that Voros coefficients are expressed as the difference value of the generating function of the free energies with respect to parameters. And second one is, as its applications, we get the explicit forms of the Voros coefficient and free energies. So thank you for your attention.
Questions and comments?
Thank you very much. I have a very naive question, which is the naming of the index G. Is that related to genus in some way? Because you're talking about topological recursion. Is there a topology by which we are?
Yeah. So Fg equals to WG0. So this WG and this G.
Sorry, I can't see what you're pointing to.
Oh,
Could you use the cursor or?
So Fg
yes.
equals to WG0. So this G is the genus. Yeah, genus. So so the topological recursion. So so oh.
It's the gum.
Thank you. So
Mm. Mhm.
You're telling us that, to answer Nadine's question, that G means genus,
yeah.
and that's why this is topological recursion.
Yeah.
If you had said this at the beginning, it would be clearer to those of us who are not experts. But thank you, it's clear now.
Oh, yeah. Sorry. Thank you.
More questions or comments?
May I?
Something.
Yes.
Go ahead, Enrique.
Yes, I too, I'm not very familiar with the topological recursion. So my question is, for the Gauss hypergeometric equation, you said that a certain admissibility condition is not satisfied, right?
Yeah.
How does that?
For the Gauss hypergeometric.
Yes, for the Gauss
Yeah.
equation. How does that affect your presentation then? I suppose if they wrote such an admissibility condition, it means that it is necessary for something. So,
Sorry, pardon?
yes, I suppose if there is an admissibility condition in the theory of the topological recursion, it has a purpose.
Quantization. We use the admissibility condition using the quantization. So
Yeah, yes.
So this theorem 4 is the Bouchard and N result. So for the 1-1-1-2 curve, satisfy the admissibility condition of the Bouchard and N, and so we can find the psi is the WKB solution of the equation. But
Yes.
but the Gauss curve does not satisfy the Bouchard and N so admissibility condition. So we haven't from the Bouchard and N result, we cannot obtain the differential equation.
Okay. Thank you.
Sorry.
Thank you very much.
Okay, let's thank Yumiko again. Please remember, there's a welcome wine reception at the Newton Institute at 5 o'clock. Everybody's welcome to come.